Okay, this is the beginning of chapter 15 lecture on equilibrium. And chemical equilibrium occurs when the forward and the reverse reaction proceed at equal rates. So we'll take something really simple. If we take the decomposition of the N2O4 gas and it turns into 2NO2 gas, this is considered an equilibrium mixture. And the reason that it is an equilibrium mixture is because the reaction is reversible. The way that you recognize a reversible reaction, one that is in equilibrium, is with these double arrows. They're either two regular double arrows or just this half of a head. So let's say we have two elementary steps going on here. We have N2O4 turning into 2NO2. And so back from chapter 14, if I were to write the rate expression for that reaction, it would be equal to the rate is equal to the K constant for the forward reaction times the concentration of the N2O4 at any point in time. And then the rate of the reverse reaction would just be that reaction from above flipped around, and it would be the rate is equal to the K constant for the reverse reaction times NO2 raised to the second power. Remember, when we have an elementary reaction, an elementary step, we can say that the order of the reaction is just the coefficient in front of the reactant. And so that's why we can put a 2 there. So since by definition, equilibrium is when the rate of the forward reaction is equal to the rate of the reverse reaction, if these two values are equal, according to the definition, then this Kf times N2O4 should equal Kr times NO2. So now, if we look at that in terms of a ratio of the K of the forward reaction to the K of the reverse, we have this expression, which is just algebraically manipulating this equivalence. I get NO2 squared over N2O4. And we call this ratio of the rate of the forward reaction to the rate of the reverse reaction. The rate constant for the forward reaction over the rate constant for the reverse. We call this the equilibrium constant. And now it's important, just like K values are specific at a specific temperature, equilibrium values are specific for temperature as well. Typically, we'll talk about them as 25 degrees Celsius. So if we were to look at how the concentration of the reactant and the product change over time, so this is a graph of concentration versus time here. And then if we look at how the rate changes, we see that as the reaction progresses, as you get less and less of the N2O4, the rate of the forward reaction decreases as the rate of the reverse reaction is increasing, and eventually at equilibrium, those two rates are equal at the same point on the graph. So we know that equilibrium would be achieved at this point in time. Whereas here's that same point in time on this graph, which is our concentration versus time. And we can see that those components are not the same as they are here with the rate of the reaction. Okay, so now we'll take a look at an equilibrium reaction that's pretty important, pretty common. It's the Haber process, and it's critical in the production of fertilizers at high pressure and temperature, and it's a catalyzed reaction. Anyway, we take nitrogen and hydrogen gas, and from that we get ammonia, which is a component of fertilizers. And so we see the double arrows here that indicates it's an equilibrium. So regardless of what we start with, We could start with the ammonia and achieve equilibrium. We could start with the nitrogen and hydrogen and achieve equilibrium. That's an important point in an equilibrium reaction. So we want to get what we call an equilibrium constant expression. That's what that represents, equilibrium constant expression. And the equilibrium constant expression depends only on the stoichiometry of the reaction, not the mechanism. So the Kc, which is the equilibrium constant for the concentration, is equal to the concentration of the product raised to the power of the coefficient. There we can see the product and the coefficient, divided by the concentration of one of the reactants, the N2, times the concentration of the other reactant raised to the power of the coefficient. So this here is not the order. This is the coefficient from the stoichiometry of the reaction or the balanced reaction. So that's the way you would write an equilibrium expression. Here's another example. Nitrogen monoxide reacting with chlorine gas, and we get NOCl. The expression, which is Kc. Kc is the equilibrium constant for concentration. We'll also talk about Kp later, which is related to the equilibrium constant for pressure. But the Kc for concentration for this reaction is going to be my product, NOCl, raised to the power of the coefficient 2, divided by the concentration of the nitrogen monoxide, raised to the power of its coefficient, times the chlorine gas raised to its power of the coefficient, which would just be 1, so I can just leave that out. I'm going to stop right there.